Okay, good morning, everyone who is present. It seems to be just one more. All right. So soon we will start. Okay, so we will continue with what we wanted to do. And this is where we had stopped, I think, this exercise. And in this exercise, you also need to sort of know about how to use non-singular linear transformation to find the PDF of joint PDF from the domain to the range. That I will give you the formula later. You also would have studied earlier how it changes with the linear transformations, non-singular linear transformations. Okay. So this we will also see today. Now, yeah, we look at conditional expectation y given x, where this x can even be a vector valued random. So we just indicate it is basically one can imitate the one-dimensional case. So note that this is a vector. However, this y is a scalar. So one begins with, in the earlier case, we began with x comma y. Now we have to begin with the vector x comma y. So let's say x is an Rm valued random variable. So x1, x2, xm are the coordinates. So x1, x2, xm comma y be a m plus 1 dimensional continuous random variable with joint PDF, this notation. So this is a function on R to the power m plus 1. So the marginal PDF of x bar, or rather x under bar, underline is given by just you would have seen it in your probability course. It is just that you integrate out the y variable. So take the joint density of x bar and y and integrate out the y variable. So what you get is the function of the other m variables. That precisely is the marginal PDF of x underline. Yeah, note it down if you want. Now suppose expectation of y exists. Then sort of following similar notation, m of x bar, x is a vector here in our Rm, conditional expectation y given x bar equal to little x bar is precisely this expression. Integration over R, y times the conditional probability density of y given x, and that precisely is this. Whenever, of course, this is non-positive. Otherwise, this itself is taken to be 0. So the random variable conditional expectation y given x bar is defined by this thing where this x little x you substitute with x bar omega equal to x bar. So that random variable is defined in this fashion. So note that the conditional expectation of y given x bar is a one-dimensional random variable. And as in the earlier case, what can show that whenever expectation of y exists, expectation of the conditional expectation y given x bar is precisely expectation. Note it down if you want. Well, a natural question here is, can you make this y also to be a vector? Well, it is in general not a very useful concept because of the following reason. If you recall our this thing with the discrete case, one of the main motivating reason for defining conditional expectation as a random variable was to study martingales. And in the study of martingales, you remember we also introduced super martingale and sub martingale. And in that case, the equality relation in the definition of martingale, that crucial equation, is substituted with appropriate inequality. And that kind of an inequality for vectors, you cannot really have a well-defined meaning. Because Rn is not sort of linearly ordered. And the case of martingale, for example, there are martingales. If x is a martingale, then you know that x squared, which makes sense also, and that is a submartingale, and that has been a major, let us say, object which helps in the study of martingales. Okay, now just as a interesting digression, we will look at least squares prediction. So, which again you might have seen in a directly or in subtle fashion in statistics course. So when we talk about, so now we are back to, let us say, considering when y, x, they're all, let's say, scalars. So in our discussion on conditional expectation of, let's say, y given x, this x is sort of assumed to be a known variable, or let's say you have some information concerning x, that is given x. So based on that, you want to say something about how, what can you or what can you say about y? So if you consider this as a random variable, this amounts to making some kind of a prediction about y. That is the expected behavior of y given x equal to something, or x takes value somewhere. Yeah. So since we only know x, any predictor of y is going to be a function of x. So let us say g of x. If what you want to predict on the basis of known information, it has to depend on the known information. And a mathematical way of saying that is going to be a function of x. And how would this function be? What would you like it to be? We would like this to be as close to y as possible. Which means as close to y as possible means you should have a way of measuring the distance between y and g of x. And one notion of this distance, which has proved to be very useful in various branches, in statistics, for example, and also in various approximation results, you will be coming across in functional analysis and various things, is the means, the L square distance, L2 distance, or to use the statistical terminology, mean square error. So if you put d of g as, let's say, the expectation of y minus g of x whole square. Of course, this would mean that we need to assume a priori that y is square integral. And also we need to consider this g of x, which is also square integral. So this is a measure of the error or imperfection in using gx for predicting y. Of course, ideal circumstances, this should be 0, which means you have very good. That means y is equal to gx is a very desirable thing, but that would make y itself to be a function of x. So in principle, in that case, if you know x, you know everything about y. In particular, if y is equal to x, for example. So that we know that conditional expectation x given x is x itself. And at the other extreme, you have, if x and y are independent, the conditional expectation of y given x is expectation y. You don't get any information more than what you already know, namely expectation of y. I mean, that also sort of gels well with our intuitive notion of independence. Yeah, so clearly one would like to choose gx such that the mean square error is the least. Okay, please note it down if you want to. All right. So one elementary lemma. Let z be a random variable having finite second moments. So in particular, the expectation exists. And of course, the variance also exists. So let us denote by mu the expectation of z. Then for any constant a, real constant, expectation of z minus a whole squared is expectation of z minus mu whole squared plus a minus mu whole squared. So if mu is equal to a, this is this guy, which is independent of a, so that is the minimum. This you would have studied in your basic probability course. This minimum is attained, minimum is at when A is equal to A. See, this you can prove by using calculus, very simple, but we want to give this proof because we would like to make use of this expression, that equality. Proof is very simple. For any A, A is, let's say, given arbitrary. In this, you write in this fashion. Subtract and add mu. And it's just elementary algebra. So that gives you this expression. And in this expression, the minimum is attained if A is equal to mu. Okay. So we will now state this theorem. Let X and Y have finite second moments. Set D of G equal to expectation of Y minus GX whole square whenever this makes sense. That is, expectation of GX squared is finite. So then for any little x in the range of x, the minimum value of this is attained when that function is the conditional expectation of y given x equal to capital X equal to little x. So if you are to consider this as a function of little x, that is a random variable. So this statement says that the least squares predictor of y is the conditional expectation of y given x. Proof. So as this has finite expectation, by our earlier results, this expectation of y minus gx whole squared is expectation of the conditional expectation. So we will look at the conditional expectation of y minus gx whole squared given x equal to little x. Please note it down if you want to. So let little x be arbitrary in range of x. So we know that this little f of y given x equal to x is a PDF as a function of y. So since we have that m of x is conditional expectation of y given x equal to x, which is precisely integral over y, f y given x equal to little x dy. By the preceding lemma, we get this. That is using it for integration with respect to this probability density function. That is f y given x equal to little x. So there, this g of x plays the role of a constant, a. So this g at little x plays the role of a in the notation of the previous lemma. and m of x is plays the role of, because of this, the role of mu, because we are considering here the random variable this thing concerned is the conditional probability. So the minimum is attained when g of x is precisely equal to mx. Sorry, note it down if you want to. Okay. So the minimum is attained when gx is this. So therefore, one concludes that this is minimum when g of capital X is the conditional expectation random. And of course, since we know that expectation of conditional expectation is expectation of y, in the language of statistics, it also follows that the least squares predictor is also an unbiased predictor. So in the language of, let's say, functional analysis, you can say that, say, this is the L2 distance between y and gx if you are in L2 of, let's say, the basic probability space. And if you are familiar with conditional expectation with given a sigma algebra and so on, you know that conditional expectation is a function of x, which means it is a function of x. So the subsigma algebra that one takes is all the sigma algebra generated by this capital X. So you take L2 of those square integrable functions, but which are measurable with respect to the sigma algebra generated by X, and that is a closed subspace of the big space L2 of mu, L2 of omega A mu. A is the full sigma algebra. So L2 of all square integrable functions which are measurable with respect to the sigma algebra generated by X forms a closed subspace in the L2 space. And you know from your results in functional analysis, if you take a point in the big space and project it onto that subspace, the thing which attains the closest point in the subspace is the projection. So what this result translated in that language is, if y, x, they are all square integrable, and then you take the closed subspace L2 of all functions which are measurable with respect to the smaller sigma algebra, that is the sigma algebra generated by X, then the projection onto that subspace is precisely the conditional expectation random. So naturally, it minimizes the distance. Note it down if you want to. The previous slide is this. Okay. So far, we have been seeing X and Y where both X and Y also happen to be continuous. One can also have situations where X comma Y is a two-dimensional random variable, but X is discrete, but Y is continuous. So this kind of a situation will typically happen when, for example, X has a discrete distribution with some parameter. But the parameter itself may be a random variable, which is a continuous random. So in such cases, X comma Y where X is discrete and Y is continuous and so on, that to take care of such situations, one cannot have a very general theory, or if you can have it, if you have measure theory, but to be able to do some computations and things like that, okay, we will just look at an example. Because we will also see such a situation later on. So this example, suppose the number X, which let's say denotes the number of red corpuscles in unit volume of blood. Empirically, it has been found that that follows a Poisson distribution. Poisson distribution is one of the, let us say, distribution favored by nature. You will soon see in the when we do Poisson process. So let's say the parameter, so any Poisson distribution is the parameter, real, I mean positive parameter. Let's say that Y occurs according to a continuous random variable Y, let's say having an exponential distribution with known parameter, let's say 1. So with this information, the first thing one should try to do is what kind of values the two-dimensional random variable X comma Y takes. So since X has a Poisson distribution with a certain parameter, that will take value in non-negative integers, 0, 1, 2, etc. And this has an exponential distribution, so it will be taking value in the infinite interval 0 to infinity, open interval. So if you draw a picture, this thing, it will be just a collection of parallel lines to the y-axis. Each line would be separated, I mean, each adjacent lines would be separated by a distance of 1 because of this. I mean, we are drawing it as X comma Y. So the range of this two-dimensional random variable is a union of denumerable countable number of disjoint, well-separated parallel half lines. You can draw a picture as you are listening to this rough diagram. Okay. So clearly, this is neither discrete nor continuous as a two-dimensional random variable. So the information we have is that from what we have here, if y is known, then this has x has a Poisson distribution with that parameter y. So probability capital X equal to k with given capital Y equal to little y is this is a Poisson mass function. Y to the power k divided by k factorial, the whole thing multiplied by e to the power minus y. K varying over 0, 1, 2, etc. So this y is a parameter. So now we proceed by imitating similar steps for two-dimensional discrete or continuous random variables. These things can be justified easily because the range is a nice set. It's a set that one can easily handle. So now you can using that all the proceeding similarly, etc., imitating the procedure we know already. So probability x equal to k is, so you know the marginal density of y, you know, that is exponential with parameter 1. So conditional probability x equal to little k given capital Y equal to little y, f sub y, y dy. You are given this expression, probability x equal to k given y equal to y. That is this one. And exponential density, you know here. And do some elementary manipulations to get this. So basically, you have to convert this into your expression you can handle. The fashion in which these things are written, it suggests a gamma integral. And makes a change of variable, say z equal to 2 times y. So you can express it in this fashion. And this integral, indefinite integral, is precisely gamma of k plus 1. And gamma of k plus 1, k is a positive integer or non-negative integer. So you know the value of gamma k plus 1. So do the necessary cancellations, then you get 1 divided by 2 to the power, or rather half to the power k plus 1. So probability of capital X equal to k is this, and this you easily observe that you can write it in this fashion so that you conclude that capital X has a geometric distribution with parameter half. So this is a kind of toy example where you can easily compute these guys. Okay. Yeah, note it down. All these, all the arguments, please verify yourself. So let me recall a result which you would have already seen in your basic probability course. So non-singular linear transformations of continuous random variables. So let capital A be an n cross n matrix with real entries, and it is non-singular. So that is determinant of A is not 0. So A inverse exists. And whenever we talk about a vector random variable, invariably we treat it as a column vector. This is a convention we generally make. So that one can talk about the transformation is A applied to X, or rather A multiplied with X as a matrix multiplication. So the way we are writing x1, x2, xn, it denotes generally a row vector. So that is why we, in this case, I make it a special this thing to put the transpose. So considering that this way, it has an advantage that we can write it, the composition this way, so that the things which this is a more easier form to sort of handle than row multi, considering that's a row vector. So define y bar as A applied to x bar. So this will again be a vector valued random variable. So if you denote the components by y1, y2, yn, so y bar is y1, y2, yn transpose. So then you can easily see that yi is given by this for each. Then the Rn valued random variable y bar is also a continuous random variable with probability density function, which let us say f sub y bar. So that is given by this expression. F sub y bar at y1, y2, yn is the reciprocal of mod of the determinant of A, 1 over mod determinant A, f sub x at x1, x2, xn, where this vector x is basically the inverse image of y under A. Or basically you can say that x1, x2, xn is the unique solution to the system of linear equations. So we may write this in a shorter form. F sub y at y is 1 over determinant of mod of determinant A. F sub x, A inverse. You must have used this in your earlier course. I don't know whether this was proved. Maybe those of you who have done measure theory might have seen a proof. Usually this is derived as a corollary or a special case of the general Jacobian formula concerning change of variables for smooth functions, certain smooth functions with satisfying certain conditions. And that formula itself is derived from the so-called inverse function theorem in analysis. Since this is a linear transformation, the Jacobian of the linear transformation is precisely the matrix, then determinant of the matrix itself, or the matrix which determines the linear transformation. For a proof for basically non-singular linear transformation, you can look up Apostle's book on mathematical analysis. Which again uses measure theoretic ideas. So this sort of finishes our review of continuous random variables and so on. So in the next class, we will start with Poisson processes. So if you want me to go back to any of the slides, I can do that. So this I will put up on the Moodle today itself. Okay. All right. So now, just wanted to make some comments. So those of you who have taken measure theory would have seen some proof, and yeah. So in your analysis course, you might have done inverse function theorem. So this follows as a consequence of these things. So however, a specific proof for linear transformation is given in Apostle's book, where any linear, non-singular linear transformation is taken as a composition of three kinds of elementary transformations. In those cases, it is easy to calculate these things. And a result from linear algebra which says that any non-singular transformation can be written as a composition of such maps. So using that, but very often this is in the 2 by 2 case, you can easily show it, but generally n by n, it is like that. And if you are willing to assume a lot of smoothness assumptions, then it is, and also the assumptions of the inverse function theorem, which of course will be satisfied in the case of linear transformation. This follows from a result inverse function theorem, which you would have done in your, I think, I don't know in which calculus course. Did you see in your calculus course that is a vector calculus course is usually done in the third semester, I think. Inverse function theorem.
It's an analysis.
Analysis. Inverse function theorem you would have seen in your calculus course, I think, right?
No, calculus was majorly Riemann integration for functions from Rn to R and that on that.
No, that course was called, let us say, what did Professor Ramadas teach you?
Yeah, Ramdas was calculus.
Yeah, because that course in CMI, it is called calculus. That's why I asked.
Right. But we saw inverse function theorem in analysis 2. That was Pramad's course.
Analysis 2. I see. Analysis 2, at that time, you might not have this thing to prove the theorem, I think. I don't know. Something would have been assumed at some step.
No, I think we more or less proved the.
Anyway. And also in your PDE course or optimization courses also, this will be assumed. All right. So anyway, so you can, if you have done a measure theory course, you would have seen transformation of random variables or measurable functions, integration and the transformations. So there also say how the Lebesgue measure changes under linear transformations. So then in that context, one can also prove this result. You can take a look at Apostle's book, Math Analysis. So we will stop for the day and meet again on Wednesday. Okay, so I will end the session unless you have some queries now.
Thank you, sir.
Okay, thanks a lot and take care. We will see you on Wednesday.
Thank you, sir.